We really need to just take a minute to appreciate this guy. He had a silly hat. He's got a smirk on his face. What more do you want? Okay, so I'm going to talk about the divergence theorem today. This is really a fantastic theorem, and it is the culmination of your 3 years of studying calculus. So congratulations to you students. Hats off if you've made it this far. This really is an achievement, and I'm proud of you. Pat yourself on the back. You deserve it. I'm not being sarcastic. That sounded sarcastic. I'm not being sarcastic. So to motivate the divergence theorem, I want you to imagine a lantern. Has anyone ever been camping before? The way it works is there's kind of a metal sort of screen, and you pump gas into the screen, and then when you ignite the gas, the burning gas heats up the metal mesh, and that puts off light, and then you can see and play cards or do whatever it is that people do when they go camping. And the concept here is pretty simple. If you were pumping gas into a region and then you were also vacuuming gas out of a region, then just like in our examples with the water table from Green's theorem, you could make a relationship between the rate at which gas was passing through the boundary if you knew the rate at which gas was being added to and subtracted from the region. The concept is if you added up all of the sources and the sinks on the interior of the region, then that is going to give you the flux through the boundary of the region. Okay, and here it is. So that concept just leads us directly into Gauss's divergence theorem. So we're going to consider an appropriately smooth function and an appropriately nice solid with an appropriately nice boundary. So we have to satisfy all the assumptions in order for this theorem to work. On the left-hand side of this equation, I have a surface integral, and this is the projection of the force field onto the vectors that are normal to the boundary. So that makes this the flux. And then on the right-hand side, this is the integral of del dot f. Remember that del dot f represents the divergence of f. So if you're trying to calculate the flux through a boundary, if you instead calculate the sum of the divergence everywhere on the interior of the solid, then you're guaranteed to get the same number. On the left-hand side of this equation is a surface integral. There's a lot of things that I don't want to do with this. I don't want to calculate normal vectors, and I don't want to calculate surface area differentials. On the right-hand side of this equation is a bunch of very easy things to do. Remember, del dot f involves taking partial derivatives, so I should expect, if I have like polynomial equations in my vector-valued function, I should expect this process of del dot f to make things more simple. Also, dv at the end of this just could not get any easier, right? We can use Fubini's theorem. Okay, I just need to briefly address why this theorem is true. I think you're very familiar with this argument already because it's basically the same argument that we made in Green's theorem, except now it's going to be 3D. So I'm going to imagine partitioning this solid into a bunch of little boxes, and I'm going to call them dv1 and dv2. And what we're trying to do on the right-hand side of the divergence theorem is add up all of the divergences on the interior of the region. So what we need to do is ask ourselves, in each one of these little boxes, dv, how much of f is a source or a sink? If you observe that the normal vectors to these two adjacent boxes that I've drawn to each other are just exactly in the opposite direction, so the divergence will cancel out for these two adjacent walls of the box. So everywhere on the interior of the region, all the divergences will be canceling out unless the small box does not have another little box that's adjacent to him. And so all the boxes that are on the boundary don't have an adjacent box to them. So if you add up all the divergence on the interior of the region, then you're just going to be left with the flux through the boundary of the region. Okay, so I'm going to use Gauss's theorem to solve this problem about calculating the outward flux of this rather complicated looking force field. And then I give us this really easy to use surface here. I just picked some numbers 7, 8, and 9, they're just kind of symmetric. The first thing I need to do is calculate the divergence of F. Recall that the operator del is an operation that has partial derivatives in each of the coordinates. And doing dot products is super easy, right? You just kind of like distribute each of the parts and then add them all up. Okay, so that was easy. I got the divergence already. So all I need to do is integrate this divergence over this solid, but the solid is just so easy to deal with. We're seriously almost done with this. Okay, so the divergence theorem tells me to put the divergence on the inside of the integral, and then here at the end I have dv. I've chosen to do dz dy dx. So z is going to go from 0 to 9, y is going to go from 0 to 8, and x is going to go from 0 to 7. So that's it. I mean, what a fantastic theorem. This could not be any easier. If we were going to do this without using the divergence theorem, then what we would have to do is find a normal vector to each one of the faces of this box. Each one of these normal vectors, we're going to have to project the force field onto that normal vector. Then we're going to have to integrate that projection over every point on the surface. Given the choice between doing 6 different surface integrals and one like super easy triple integral, we name this very, very important theorem after Gauss as a kind of way of honoring him. You know, this theorem is in some sense the most important theorem in calculus, and in some sense he is one of the most influential figures in mathematics. So now I'm going to calculate the divergence of this field through a kind of cylindrical surface. Okay, so I found the divergence of this kind of very exponential force field. Okay, and now I don't want to set up this triple integral in rectangular coordinates because it's obviously a cylinder, so I'm going to use cylindrical coordinates. Yeah, you can see where I got all these pieces from. You know, z is going to go from 0 to 3, r is going to go from 0 to 1, and then the cylinder goes all the way around, so theta is going to go from 0 to 2 pi. If I would have changed this problem and I would have put something like x to the power of 10,000, when I calculated the divergence, this z partial derivative of the p coordinate of the vector valued function just would have annihilated this x to the power of 100. So it's kind of strange. Sometimes when you think about this, the interpretation is that you're going to get the same answer for a bunch of different vector valued functions because this process of taking partial derivatives eliminates a lot of information. The one other thing that I want to point out is it's really tempting to do this, and I confess that I'm guilty of this as well, is to try to use the divergence theorem when you have a function that's maybe something like negative x over x squared plus y squared plus z squared to the 3/2 power. And then to like integrate this over a sphere centered at the origin. Remember that the assumption is that these partial derivatives are continuous and exist, and f is undefined at the origin, right? I mean, if I put 0 squared plus 0 squared plus 0 squared, I would get 0 over 0. So you got to be careful with the divergence theorem. These assumptions really do matter, and you really will get nonsense answers if you try to use it in situations where it doesn't apply. Okay, I want to leave you with kind of an interesting thought experiment and math exercise here. Think about this vector valued function, which we've seen already represents the force due to gravity in 3 dimensions. And we're going to assume that we're at some place that's far away from the origin, so that this function is defined and does have continuous partial derivatives everywhere. And then go ahead and calculate the divergence of this function and see what you get. I'm not going to tell you the answer, but it's really neat. I'm just going to tell you that functions that do this, once you do the exercise and you get the answer, I'm just going to tell you there's a really cool word when this happens. These functions are all called solenoidal. So I don't mean to try to trick anybody. I'm really not like dropping hints about what's going to be on a test or anything like that. I swear this is just for your own interest. This is just a fun thing to look up. Think about why this force due to gravity should be solenoidal. I mean, you're going to need like 5 whole minutes to do this homework assignment because the divergence theorem is so easy to use. And let me know if you have any questions.